Welcome to my new calculus channel. My name is John Gabriel, and today I'll be discussing the next in my series, What You Had to Know But Your Ignorant Teachers Could Not Tell You. Now, in the previous video, I jumped ahead a few hundred years, but I'm going to be resuming from part 25. So going back to where I started deriving everything in mathematics. So now remember that I showed you how the ancient Greeks started with magnitudes and ratios of magnitudes, right? So anything that mattered had to do with ratio. And if you couldn't do anything with the theorem or some kind of knowledge that was realized, chances are that it didn't have ratio in it. So ratio is used to measure everything from calculus to ordinary mathematics to arithmetic operations to probability to calculating areas, volumes, everything. Okay, so the first kind of ratios I showed you were the ones where you compare lines, right? And then I showed you how you could start deriving numbers by assigning a special magnitude to be the unit, right? And then from the unit, you would start giving names to those magnitudes. So if the abstract unit is called 1, then 2 units next to each other like this would be 2 and 3, etc. And then I showed you how you form ratios with the numbers, right? Okay, and finally, this resulted in rational numbers. I also discussed those magnitudes that have no ratio which describes them in terms of numbers. So for example, pi is the circumference length over the circle diameter, but at least one of these has no measure. So for example, if the diameter is a rational number, then this is an incommensurable magnitude, okay? And if this is a rational number, the circle length, then the diameter is an incommensurable magnitude, or both can be incommensurable magnitudes. But there is no ratio where both the numerator and the denominator are integers, okay? So in other words, there is no number that describes pi because the only numbers are the rational numbers. There is no such thing as a real number. It's a myth, and I've explained that in several previous episodes. So ratio appears in every subject, and it will come up in every useful area of mathematics, science, technology, and engineering. In none of those fields will you find any of the theoretical rot that you find in mainstream academia. And when I mention rot, I'm thinking about real analysis, topology, metric spaces, which is part of topology, and pure abstract algebra, or in some respects also group theory. Now, this is what I would like to see mathematics being based on, and I'd like to see mathematics education return to the beauty and the light and the usefulness that began with the ancient Greeks. Now, Newton, by the way, who was about 320 years ahead of his time, and the reason I say 320 years is that he was born 320 years before me. And Newton was not able to solve the tangent line problem, but I was. So you say, what's the big deal? Because he was a pioneer. This is true, but Newton did have the tools to resolve the tangent line problem. He failed because he didn't know Euclid's elements. He didn't study the elements of Euclid as he should have. If he had, he would have been able to devise the general proof for the derivative, which is in terms of similar triangles, and he would indeed have come up with the new calculus definition, which is this, okay? And I think you've seen this before, but if you haven't, the free download book that I shall provide in the link, the most important mathematics book ever written, describes what all these not variables, but what all these names mean, n, m, x, etc. Okay, so now you'll notice now that this derivative is still a ratio. See, this is a ratio, okay? And there's no need to do stupid things like you see in mainstream mathematics by putting that in front of a finite difference. That's flawed. Okay, so there's no need to do nonsense like this. Okay, and there's also a new definition for the integral in the new calculus, and that's also described in the free book. But now Newton was an extremely intelligent guy, and he did use things like slope, rate, derivative, mean value, even though he didn't know it was a mean value, and many other ratios to measure different things. And he even began his study of calculus with finite differences. So a first order finite difference is written like this. The document you're looking at in front of you is called How He Got Calculus, and it's very, very interesting. If you want to understand how he got calculus and get a glimpse into the mind of Newton, this article here, which is about 20 pages long, will tell you everything you need to know about how Newton thought and how his work was continued through James Gregory and Taylor and Maclaurin and all the other mathematicians that came after him. So you'll also see how he discovered the interpolation polynomial in terms of finite differences. And there's a lot of historical information in this article, which I think anyone who wants to learn mathematics and understand it should actually know. And so I would advise that you download this also free. I will put a link to it, and you can study it in your own time. Now, the Gabriel polynomial is far superior to the Taylor polynomial, and I give you an example of it over here. Newton would have loved to see this, and Newton would have loved to see how I resolved the tangent line problem. So anyway, everything in mathematics that is of any value has to do with ratio, okay? Everything is ratio. The arithmetic mean, which is the second most important concept in mathematics, right after ratio or number itself, is the reason we can calculate areas and volumes and hypervolumes in calculus. Okay, you couldn't do it without the arithmetic mean, because literally, as I've shown you in the past, the area under a curve is actually the product of two arithmetic means. And I'll cover that again sometime in the future in more detail, but I'd like to keep this presentation simple for the time being. So I just wanted to show you that everything we do in mathematics goes back to the ratio, and the first ratio was a ratio of magnitudes, like you see over here. Get my pen up. Like you see here, a straight line compared to another line, right? This was a ratio of magnitudes. There are so many things I want to cover. I would like to talk about how Newton discovered his physics formulas. And I have a lot to say about that, but haven't gotten around to saying anything about that. I have written a very important article on time. In fact, the first and only well-formed definition of time. I will put a link to that article in my details section, because when I do begin discussing some of Newton's ideas, you'll need to understand what is time to be able to appreciate how Newton arrived at his formulas. For example, V is equal to U plus AT, etc. Okay, and how he realized calculus in order to solve these problems, and a lot more than that. So I hope you've enjoyed this little presentation and that you will subscribe to my channel and spread the news of this channel and join me again soon in the near future. So I'm running out of time. Till next time, this is a new calculus channel. I'm John Gabriel. Goodbye.